In this video, I will introduce you to what would happen when we make changes to a system that is already at equilibrium. After we briefly discuss this, we will lead to a very important topic in VCE chemistry, which is the Chatelier Principle. This principle is heavily assessed in the exam. So let's have a look first. So imagine we have a hypothetical reaction. A plus B goes to AB. And just a little bit of revision. If we start off with only particle A and particle B, then we only have forward reaction. And as we are producing more and more product AB, we would get collision between AB particles or molecules. So we would actually produce A and B. So initially we only have forward reaction. As we use up A and B, we have less collisions between A and B, which reduces the rate of forward reactions gradually. As we have more AB, we get more collisions between AB molecules, which means we have more successful collision between AB molecules. So the rate of reverse reaction gradually increases until we get to the point where the rate of forward reaction is exactly equal to the rate of reverse reaction. We are at equilibrium. So the rate of forward reaction gradually decreases, the rate of reverse reaction gradually increases, and then here we reaches equilibrium. So what would happen if I add the particle A at equilibrium? So if we are in a gaseous system, I have pumped in lots of gas A. If we are an aqueous solution system, I have added some A solution when the equilibrium is being established. What would actually happen? So let's think from the rate of reaction perspective. We have more particle A. So even if the amount or number of particle B stays the same, we would still have more collisions between them. So the probability of A and B collide into each other would increase. So the rate of forward reaction should increase. Rate of forward reaction increase, which is depicted as this sudden increase in forward reaction. And then we get a very similar story. So as we use up AB to produce particle AB, then forward rate would decrease. Since we have more AB, the reverse rate would increase. So the forward rate would decrease and the reverse rate will gradually increase until we meet at a new equilibrium. So we eventually reach this new equilibrium again. But note that the rate of both forward and reverse reaction is actually higher at the new equilibrium. So why is this the case? Because simply you have more A at equilibrium. So overall, the amount of particles in your system have increased. And what happens when you have more stuff in your system, you get more collisions. When you have more collisions, given a particular temperature, which is we assumed is unchanged, then we would expect to see a higher rate, because if the percentage of successful collision is unchanged and you have more particles, then you get more collisions. So you get more successful collisions. So you get a higher rate of reaction. And this is completely okay. We are still at equilibrium. Because the definition of equilibrium is where the forward reaction is equal to the rate of reverse reaction. Doesn't matter when both forward and reverse reaction occurs at a faster rate, as long as they are equal to each other, then we are at equilibrium. So this is the perspective from rate of reaction. We can also think this a problem from the perspective of your concentration fraction. So remember, QC is product raises to the certain power divided by reactants raised to certain power. Maybe I should call this Y because they tend to be different. So if you add reactants, in this case, if you add A, you are increasing the concentration of reactants. So this means your QC should decrease. And remember before that we are already at equilibrium. So initially QC equals to Kc. And now, because QC is getting less, it is smaller than Kc. So somehow we need to increase QC in order to make it the same as Kc again. How do we increase the concentration fraction? We need to increase the concentration of product and decrease the concentration of reactants. Thus, we favor the forward reaction. Which is exactly what we said when we think about from the collision theory's perspective. So you get the same result ultimately. If you add products, if you add AB, for example, you will increase QC, making it bigger than Kc. So you need to somehow decrease QC by producing more reactants and use up some of the product, which means you are favoring the reverse reaction. So what happens when you change concentration? By changing volume. So in this case, we are changing individual reactants or products concentration. But when we change volume, we change everything. So we change the concentration of everything in the system by the same factor. So note it is by the same factor, not the same magnitude. So 2 times 2 is 4, 1 times 2 is 2. So the factor is 2, but we have, in this case we are adding 1, in this case we are adding 2. So not the same magnitude, but the same factor. And this really depends on the specific reaction. So you have A to the A, B to the B, C to the C. If you have this scenario, and then you double everything by half the value, then whether QC increases or decreases really depends on the magnitude of A, B, C, and D, the magnitude of the exponent. So if you are raising maybe 2 to the power of 2, and divided by 2 to the power of 1, you are increasing QC. And if the exponent for this is the opposite, you are decreasing the QC. So this is really differs on a case-by-case basis. So you need to really investigate different systems by perhaps substitute in values and then see whether QC is actually getting bigger or getting smaller. And then you can work out the relative position to Kc after this change. And we know that the system wants to restore into its original equilibrium. So you can either increase QC by favoring the forward reaction or decrease QC by favoring the reverse. So this really depends on the exact scenario. So temperature is really the most interesting case. So it actually changes the equilibrium constant. So as I have discussed in the previous video, Kc is specific to the temperature we're referring to. If we change the temperature, we change the Kc, we change the equilibrium constant. So if we have exothermic reaction, remember exothermic is release heat. Combustion reactions, they are exothermic. So you are combusting coal, you are combusting petrol to release heat and release energy. So when you are releasing heat, when you have exothermic reaction, you like a cold climate. So you like cold or you like low temperature. So the way I think about this is that when do you want to have more heat? When you are in a cold temperature, you like more heat. So for this kind of reaction, when you decrease the temperature, you increase Kc. So you increase the equilibrium constant. The specific reasoning behind this will be discussed very soon when we talk about Le Chatelier's principle. When you have endothermic reaction, so when you are absorbing heat, you like hot climate, you like high temperature. So high temperature would increase Kc. So that's just the intuition. I think this intuition is very helpful for you to understand the next big topic, which is called Le Chatelier's principle. You need to remember this name, you need to remember this principle, and you must state this in the exam. So whenever you encounter questions like this, you need to state this principle in the exam. I will abbreviate this as LC principle in this video. But in the exam, you should first write out the full name. So you write out Le Chatelier's principle, and then you can write LC in subsequent mentions. So what Le Chatelier's principle is saying is that when equilibrium system is subject to a change, the system will partially oppose the change. So this is what the system always wants to do. It's like having some inertia. When you are changing something, the system doesn't like it. So it wants to go back. But only partially go back. It cannot restore to the original equilibrium. It can only try to oppose this change and actually never reaches the original state ever again. So the new equilibrium after the disruption will never have the same concentration as the original equilibrium. So there are some steps that I found very helpful when you are approaching this kind of question involving the Chatelier's principle. So step 1 is to state the change. Perhaps you are increasing the reactant in the system, but you need to state it. We now have increased the concentration of reactant A, so you need to state what you are changing. Step 2, you need to state Le Chatelier's principle and say in the system wants to partially oppose this change. Step 3. So in this case, since we have added A, system wants to reduce A. Determine which way the reaction would move. In this example, if we are adding A, the system wants to get rid of A, so it favors the forward reaction to consume A and make AB. And step 4 is to state the new equilibrium. So state the change. Going back to this instance, if we are adding A, we favor the forward reaction. So we reduce the concentration of A, reduce the concentration of B, and increase the concentration of AB. But very importantly, the concentration of A, so the reactant we have added, should be higher than the concentration of A before we added, so in the original equilibrium. Because remember, the system can only partially oppose the change. It can never restore the concentration of A back to the original equilibrium. But the concentration of B would unambiguously decrease. Because we are favoring the forward reaction, we are using up more of B. The concentration for AB would also unambiguously increase, since we are favoring the forward reaction and producing more of AB. So overall, you should say that concentration of A increased, concentration of B decreased, concentration of AB have increased. I want to repeat this again, because we are adding A and system can only partially oppose the change. So relative to before, the concentration of A would still be higher than the original equilibrium. So let's have a think. What would happen? So maybe before we talk about this point, let's draw what happens to the rate, to the concentration, and to the amount of AB and AB at this new equilibrium. So we have this system. And we are adding A. So we first look at the concentration time graph. So suppose initially we have B here, A here, and AB. So this is the concentration of B, A, and AB at the original equilibrium. The way we can tell it is at equilibrium is that the gradient is 0, so it's flat. So we are adding some A. And we know that the system wants to partially oppose A, this addition, by favoring the forward reaction. So use some of A, use some of B to produce more AB. So the concentration of A decreases, concentration of B decreases. Why does the concentration of B decrease? Well, you must consume some B when you are making AB, when you are making the product. And the concentration of AB increases. And note that the concentration of A is still higher than the original equilibrium, since we are partially opposing the change. So this is actually the same as the amount of each product, since we are not changing the volume. So the rate we have already talked about before. Original equilibrium, this is the forward decrease, the reverse increase, and then we are at a permanently higher level. So now let's look at what happens when we change the concentration of all species present in the system by adjusting the volume of the system. Changing all concentration. So this will change the concentration of every species by the same factor. As we have discussed about before, so maybe you double, you half. This is the same factor. Doesn't mean the concentration will change by the same magnitude or by the same amount. So for a gaseous system, when you decrease the volume, what happens when you decrease the volume but it doesn't decrease the amount of each gas in your system? Well, you increase the pressure. If you increase the volume, you will decrease the pressure because the gas pressure, the gas particles have a greater space to move around. So you decrease the pressure. So I will use an example to illustrate this point. So suppose we halve the volume. Then this means we double the concentration. Of all species. And remember what the Chatelier Principle says. It says the system wants to partially oppose this change. So in the exam, you say the system wants to partially oppose this change by decrease the pressure. So state this is the Chatelier Principle. How do you decrease the gas pressure in this instance? Well, let's have a look. The reactant sides have 3 particles. The product side have 2 particles. Why does the reactant side have 3 particles? You have 2 SO2 gas molecules and 1 oxygen gas. So 1 plus 2 is 3. And here you just have 2 SO3. So which side of the reaction would decrease the number of particles in your system? It's the forward reaction. So you are using up 3 particles, but only producing 2. So 3 becomes 2. So this decreases the amount of particles in your system. And if you decrease the amount of particles in your system, what you are effectively doing is you are reducing the pressure. So in order to decrease the pressure, we need to favor the forward reaction. Since it has less particles. So whenever we want to decrease the pressure, we favor the side with less particles. In this case, we favor the product side because it has 2 particles. So that's how you answer this type of questions. So now let's draw the concentration time graph. So everything doubles because we are halving the volume. So the concentration of SO2 suddenly doubles, O2 suddenly doubles, SO3 suddenly doubles. Note the magnitude of increase is the greatest for SO2 because we have more SO2 to begin with. So when it doubles, it becomes even larger. 1 times 2 is equal to 2, but 3 times 2 is equal to 6. So if you go from 1 to 2, you are adding 1. If you go from 3 to 6, you are adding 3. So you need to emphasize this on your exam. If you write all these lines as the same length, then this shows to the examiner you don't understand what is actually going on. So you are not increase the concentration by the same magnitude, you are increased by the same factor. So now you are favoring the forward reaction. So you are producing more SO3. Hence, the concentration of SO3 would increase and then stay constant when we establish the new equilibrium. Because we are using up SO2 and O2, they both decrease. Note, because of the coefficient on SO2, it should decrease 2 times as fast as oxygen. So this is the concentration time graph. The rate time graph. Let's have a look. Initially, we are at equilibrium. So the rate of forward is equal to the rate of reverse. That's why we have a one line. And we are halving the volume. So we are doubling the concentration. What does doubling the concentration do to the rate of reaction? It increases the rate of reaction. So you have this sudden jump. And you are favoring the forward reaction. So the jump of forward reaction is actually higher than the jump of reverse reaction because you are favoring the forward. And in the end, the rate is actually higher than before since we have more particles present. Although the system tries to decrease the number of particles present, it can only partially oppose the change. So it can't decrease to the original level. Same as this one. See, the concentration of SO2 and O2, they are all higher than before because we only partially oppose the change. The more difficult graph to draw perhaps is the amount of particles versus time. So the ranking is the same. Because when the concentration is higher, this means the amount is higher. Because we share the same volume of gas. But doubling the concentration does not do anything to the amount of reactant and product. You are just changing the size of your container. This have nothing to do with how much stuff you have in your container. But by favoring the forward reaction, we will be changing the amount of product and reactant. So since we are favoring the forward, we should see increase in the amount of SO3, decrease in the amount of SO2, and decrease in the amount of oxygen. Remember, the slope of SO2 should be double the slope of O2 due to this coefficient. Note, we do not have this sudden jump because we are not adding anything. We only have sudden jump in the amount if we are adding particles. So, which is what we see in this kind of example, we are adding particle A. If we are just changing the volume, we do not have this sudden jump in the amount of different product or reactant. So in the end, we have a greater concentration of SO3, greater concentration of O2, greater concentration of SO2. This happens in general when you are decreasing the volume. Because remember, we only partially oppose the change. But the amount of SO3 increase. The amount of both SO2 and O2 would decrease. This is why the Chatelier Principle is useful for industrial applications. So if you want to produce SO3 as your target product, then you should actually decrease the volume to force more SO3 being produced. So this actually increases the yield of your chemical process. So for a given amount of SO2 and O2, you are actually producing more SO3. Which is desirable because usually the products have higher economic value than the reactants. So that's the whole purpose of us trying to convert the reactants into products. So now let's look at the opposite. So what happens if volume is decreased? Then the gas pressure would decrease. So based on the Chatelier Principle, the system wants to partially oppose this change by increase the pressure. You need to state this is the Chatelier Principle in your exam. How does the system tries to increase the pressure? By favoring reaction with more gas particles. So for this type of chemical reaction, have 2 particles on the right, 3 particles on the left. We want more particles. We want to go from 2 to 3 to increase the gas pressure. So we favor the reverse reaction. Now let's look at the concentration time graph. Initially we are at equilibrium, so we have 0 gradient. We are doubling the volume, so we are halving the concentration. This one reduced to half, this one reduced, this one reduced. Note the magnitude is different. we are favoring the reverse reaction. So we are using up SO3. And we are producing more of O2 and SO2. So this is what this should look like. The rate time graph. Initially equilibrium. And this is the reverse. This is the forward. Because we are favoring the reverse reaction, so it should be higher than the rate of forward reaction. But gradually these two things converge. Also note the concentration of O2 and SO2, although they are favored, it's still less than before, since the system only partially opposed the change. Now let's look at the amount. The ranking should be the same. But we do not have this sudden drop in amount, since we are not adding or taking away any reactants or products. So because we are producing SO2, we should see gradual increase of the reactants, gradual decrease of the product. So it's very similar to the rate graph, but only that we do not have this jump or a sudden drop in amount. So what happens when we have this kind of chemical reaction? We have two particles on the left, two particles on the right. So if we double the concentration or we halve the concentration, the system cannot do anything to oppose this change. Because the system can't oppose the change, it will do nothing. So the concentration time graph, if we are doubling, just looks like this. The amount time graph will be a flat line because we're not changing anything. The rate time graph will jump suddenly and then stays there because we are not favoring any side of the reaction. But we know that increased concentration increases the rate of reaction. We can also verify this by using QC. Remember, we use concentration fraction to compare whether it's at equilibrium or not. So now is a good time to practice how to write the formula of QC. So the concentration of HCl raised to the power of 2 times concentration of H2 power of 1 Cl2 to the power of 1. So now if we double the concentration, this is the same as 4 times. And the 4's cancel out. So which is the same as before. Since QC is not changing, we know the system is still at equilibrium. That's why there's no change to the system. Remember what I said earlier. Whether QC increase or decrease when we change the concentration depends on the exponent of reactants and products. In the special case, the exponents are the same, then there's no effect. When the exponents are different, in this case, the unit is m to the negative 1, we would see something. If it's m to the 1, we will still see something. But if m to the 0, or no unit, we didn't see anything. So it just goes up immediately, and there's no side of reaction that is favored. We can change the volume of gas. We can also change the concentration. Of aqueous solutions. It's really the same idea. So if you are decreasing the concentration, the system wants to increase the concentration. But it's not realistic to increase concentration. You can add water to decrease the concentration, but how do you increase? This is very difficult to do in practice. So whenever we are dealing with aqueous solutions, we are usually doing dilution, so we decrease the concentration. So you want to dilute. This is a very important terminology. Only use dilute when you are talking about aqueous solution system. Do not ever use dilute when you are talking about a gas system, because it doesn't make any sense. Dilute means adding water to decrease the concentration. If you are talking about gas, then just say that when you decrease the volume, you increase the concentration. You increase the volume, you decrease the concentration. Do not use the term dilute. Temperature is always the most interesting topic. Based on the Chatelier Principle, if you increase the temperature, the system wants to decrease the temperature to partially offset the change. How can a system decrease the temperature? How do you decrease the temperature of a system? By favoring whichever side that gives you endothermic. Remember, endothermic reaction absorbs heat or energy from its surroundings, so it decreases the temperature. And temperature is the only effect that can change Kc. So if the forward reaction is endothermic, then we favor the forward reaction. Because we favor the forward reaction, we have more product relative to reactants at equilibrium. So we increase Kc. So if forward is exothermic, then the reverse is endothermic. So we favor the reverse, thus decrease Kc. But note, do not get confused between rate and extent of reaction. No matter which side is favored, the rate of reaction would still increase when temperature increases. So it should look like something like this. In the end, the rate should be higher. In the case the forward is endothermic, this is the forward, this is the reverse. If the forward is exothermic, you just switch the sign. So the top one becomes reverse, the bottom one becomes forward. The concentration of the species is dependent on which side of the reaction is favored. So if forward reaction is favored, then the concentration of product would be higher, and the concentration of the reactant would be lower. This is similar as exothermic reaction, it's just the opposite. So if you are decreasing the temperature, system wants to increase the temperature. So it likes exothermic reaction. So if the forward reaction is exothermic, then you are increasing the Kc. If the forward reaction is endothermic, then you favor the reverse. This decrease Kc. And regardless of what happens, the rate would decrease. Because you are lowering the temperature. So these two concepts, the rate and extent of reaction, are completely unrelated. I want to emphasize this point again. When you add inert gas, what would happen? Nothing will happen. So there's no change in concentration or the partial pressure of your species. When we are investigating chemical reactions, we only look at what happens to the gases that are actually participating in the chemical reaction. If we add inert gas, although this increases the total pressure, but we don't care. We only care about partial pressure, because partial pressure is responsible for the collision between particles, and it is the collision of particles that gives you forward and reverse reactions. If you are not changing the frequency of collision or the temperature, you are not doing anything to your rate of reaction. So there's no way that the system wants to go against your change, because you are not really changing anything important. So concentration time graph and the amount time graph is a flat line. The rate time graph is also a flat line. What happens when you add a catalyst? Catalyst only change rate, and it changes rate simultaneously. You are not favoring any reaction, so the concentration time graph is just a flat line. You are just getting an overall faster rate of both forward and reverse reaction. But you are not doing anything to your system in a meaningful way, just like adding inert gas. So this is everything I want to talk about with regard to the extent of reaction and the Chatelier principle. In the next video, we are going to talk about redox reaction, which is a very important part of VCE chemistry.